Valid word square looks like it needs a full matrix comparison, but there's a symmetry trick that cuts the work in half. You're given an array of strings called words. The task is to decide whether these strings form a valid word square, meaning the kth row reads exactly the same as the kth column for every k. For example, with the input ABCD, BNRT CRMY die, the first row ABCD matches the first column formed by the first letters of each string, the second row BNRT matches the second column, and so on. If any row diverges from its column, the square is invalid. The naive way is to iterate over every pair of indices I and j, checking that the character at row I column j equals the character at row j column I, while also guarding against out-of-bounds lengths. This double loop visits each cell twice, giving big O of n squared, quadratic time where n is the number of rows, and uses only constant extra space. It works, but it repeats the same symmetry check for both ij and j, I, doing unnecessary work. The key insight is that a valid word square must be perfectly symmetric across its main diagonal, so we only need to compare each off-diagonal pair once, and ensure every row has the same length as the total number of rows. First, we verify that each string's length equals the number of rows. If any row is shorter or longer, we can return false immediately. Then we loop I from 0 to n1, and for each I we loop j from I plus 1 to n1, comparing the character at words ij with words j, I, while also checking that both indices are within the respective string lengths. If any mismatch or length violation occurs, we return false. Otherwise, after all checks we return true. Let's trace the example. The array has 4 rows, so n equals 4. All rows have length 4, passing the initial length check. Now I equals 0, j runs 1, 2, 3. Compare words 0, 1, b with words 1, 0, b match. Compare words 0, 2, c with words 2, 0, c match. Compare words 0, 3, d with words 3, 0, d match. Next I equals 1, j runs 2, 3. Compare words 1, 2, and with words 2, 1 are, they differ, so we would return false. In the given example, they actually match, because the strings are crafted to be symmetric. Continuing the trace shows every compared pair matches, and the function finally returns true. You'll recognize this pattern when a problem asks whether a 2D collection of strings or characters is symmetric across its diagonal, especially when row lengths may vary. The algorithm runs in big O of n squared, quadratic time, because we still examine each unique pair once, and it uses big O of 1, constant time extra space beyond the input. Try the next problem, same symmetry pattern. Subscribe for more algorithm breakdowns.